Hello, my name is Anton Ilintsev. I'm from Gadget Entertainment, developer of War Thunder, a massively multiplayer online vehicle military game and upcoming online game Enlisted. And today I'm going to present you our global elimination solution, which we're going to ship in Enlisted soon. So, first about Enlisted. Enlisted is an online first-person shooter military game featuring highly dynamic environments, full time of days, huge changes in climates and weather conditions within one session, dynamic scenes with destructible environments, buildable fortifications, and quite large area. The total area is 64 square kilometers and more than that. Here on the video, it's of course not a real-time scale or full time of day cycle, but it's just to show you an idea of variety of weather conditions and lighting conditions we had in the game. So obviously not all of that happen within seconds, but all of that can be seen. There's typical for military, for shooters, first-person shooters, the details scale very significantly. The interiors features small details, and in terms of lighting, and locations are big, and the detail size is the size of the mountain or building, and all of this have to be represented somehow in any viable lighting solution. So the time of day and weather still, it's especially important to have a correct skylight because of the weather or time of day. You can see completely no sun, completely no direct lighting, or very small direct lighting on sunset or sunrise. It's important to have correct, good-looking light everywhere, in both internals and the outdoors, and the feature size is different there, and locations again is very big, and the most typical till that day solution is to have a pre-bake lighting. Most of the titles still have some kind of pre-bake lighting, and in our game it's really not reasonable solution, because there's location size, amount of time of days, and even if you multiply by only 4 time of days and 4 weather conditions, and you'll somehow interpolate, blend between them, it will at least be 8 gigabytes of compressed data, and the quality won't be actually very good, and you won't be able to change the scene, to destruct, build. The iteration cycle also becomes longer for artists. At the same time, it's important that correct light affects gameplay. Like our game is online game, multiplayer. It's important that all players see the same picture regardless of the hardware they use, the PC they use, or regardless of their position on the map. So if your enemy is hiding in shadows, he should be hiding in shadows regardless on where you stay or where you look, he's in the shadows. And that makes screen space only approach not really acceptable. It can be only used to enhance details, not as a main solution. Historically, there are a lot of ways of doing some variety of global elimination. In War Thunder, we till now use light probes. There's light maps everywhere on the market, or volume maps, which are also pre-baked usually. The issue is the compressed size of the data is quite big, and they usually pre-bake for a single time and weather. And then you either interpolate them or somehow do some stuff with that. You can also do G-buffer probes, like there are some shipped games on the market with different approaches, but the idea is simple. Instead of having the pre-baked complete light data, you pre-bake something which you can use to calculate the lighting data. For example, G-buffer of the props. There are several games shipped with that technique. Their size is still quite significant. That would be very big for our game, and it's still quite low detail, I would say. And of course, static scenes dynamic fortifications, dynamic destruction isn't really captured by this. There's a well-known voxel count tracing global elimination, which has been published. The paper has been for a lot of years by now, but I don't think there are much games shipped with that. There are a few, but not much. They do have some deficiencies, which I will elaborate later. There are virtual point lights or reflective shadow maps with imperfect shadows and light propagation volumes which can use the reflective shadow maps. Both of them features the same thing. They don't really capture skylight, which is important in our game. So you need at least do some tweaks to get skylighting, and the performance cost will increase with the light count. And typically there's one bounce. You can do multiple bounces with a voxel count tracing solution, but the performance cost will be prohibitive. So typically it's one bounce. Recently there have been some other, of course I'm not saying that that's all. There are a lot of other potential solutions, but I'm just those who are in shipped games. So there's recently been one new solution, relatively new, which kind of address the amount of compressed data you need for gbuffer probes. Instead of storing the complete gbuffer, they store shared gbuffer pixels and basically index them. That allows to have pretty real-time global elimination and with a reasonable amount of data needed. The thing is, it still requires heavy pre-compute for clever placed light probes, and dynamic destruction and dynamic fortification again is not the case because you already pre-baked that. So initially we tried to do something with the existing techniques. We tried voxel count tracing, we tried light propagation volumes, and dynamically placed light probes. We tried to compress them and enhance the quality. And we try in combination with some screen space techniques. So out of those, the most close was the voxel count tracing, because it was allowing us to have skylight and multiple lights as well. But there was some well-known for this technique drawbacks. Again, the most important would be the thin walls. In a naive brute force implementation, thin walls will bleed light. There's the way the technique works, it sample not all the rays, but statistically sample the cone, which means that when you sample, you're not really sure if it's completely the light is completely occluded by in this particular sample or not. There's a way to overcome that. For example, you can store the blocking direction information, or you can clever voxelize the scenes so to make this rarely happens. Both of these techniques are thoroughly explained in several papers, Tomorrow Children, the game, and NVIDIA XGI papers, so you can look over it. But even with that, the more tricks you get to make this work, the more performance cost you got. So, and even without that, its performance is actually for hardware is only acceptable in a, let's say, quarter resolution and with probably some temporal supersampling, because for diffuse global illumination, diffuse lighting, you need a lot of cones, even not rays, but even cones. So, but again, this was more or less acceptable in terms of the quality. With all these tricks or something, it's just if you use the tricks, then the performance is not acceptable. And if you don't use the tricks, then the quality is not acceptable. It was something close to what we needed, not acceptable though. Then we make some observation about what we have in the game. Of course, that means that your mileage may vary and your game can be different, but typical shooters have the following prerequisites, the following conditions. Light and weather change slowly. The sun, even cinematographically scaled time cycle, it still means that short-term global illumination effects are like minutes long or maybe tenths of the seconds long. So it's not very dynamic, although it has to be dynamic, but it's not very rapid, it changes. Camera movements, usually you move your camera each frame, but usually you don't move it very fast. If your character is running, it's a shooter game, right? He's running probably. It's 20 kilometers per hour. I mean, in real life, it's usually less than that, but in games, movements are typically enhanced. Even ground vehicle movements are usually like less than 70 kilometers per hour. So if the camera moves, you just don't move it far away each frame. Dynamic scenes are changing, but they're not changing. They're changing significantly. It's not a relatively small change, but they don't change very often. Building fortification takes time in any game, I guess, except maybe for strategy games, but in shooter, destruction doesn't happen very often. Usually less than once per 10 seconds or something like that. So everything is changing, but not everything is changing each frame, and not everything is changing significantly. So in the same time, general light information has to be fair for everyone, but it only has to capture the main information, like someone is hidden in the shadows, someone is under the cover. It doesn't have to be very detailed. It has to be very detailed only where you're looking specifically. That's actually well-known fact. That's the reason why screen space ambient occlusion, screen space reflection, and other screen space techniques work. They don't actually capture the real data. They only capture what is on the screen, but that means the picture you render believable and makes the technique work. So there's a lot of information available in a GBuffer on any different engine pipeline. There's albedo, normal, smoothness, whatever, and the wall positions, of course. So there's some GBuff information available in environmental probes if you have those. And with that, we decide to go for our solution, which I will completely explain later, but in a brief, in one page, we use voxel scene representation like voxel contrasting. So it's basically the whole scene, the whole world around you is voxelized like in voxel contrasting. And initially, we voxelize the scene as good as possible, but as reasonably as we can, as reasonably fast as we can. So it doesn't have to be exactly precise. It doesn't have to be like completely accurate, super sampled or whatever. It just has to be there. It just has to occlude the light and provide the first bounce at least. So we use collision geometry and the lower LODs for entities in order to achieve that. And of course, height map data. Our game in outdoors features height map. So then we feedback voxelized lead scene from the screen GBuffer. Basically, from what you're seeing on the screen, we feed back to the scene back. We use visual radiance volume map, like a lot of other solutions, and we recomputed each frame. So it's completely dynamic, and it's completely not completely, but partially recompute each frame. In order to recompute that, we use a honest ray casting, the ray traversal of this voxel scene. So there's no light leaking caused by voxel contrasting because we actually don't use cones. We just use rays as is. So that even first implementation of the idea proven to be very, very well looking and very fast in terms of performance. That gives us multiple bounds global illumination with indirect shadowing. Of course, only in place where you're looking at, which the place probably where you need it. And the average performance cost initially was like a little bit more than 2 milliseconds, but right now it's less than 1.6 milliseconds on Xbox One in full HD, so in full resolution. It can be even lower than that if you reduce the quality or use async compute, GPU compute. So in more details, for our irradiance map, we use nested volume maps around the camera, like a 3D clip map. Each cascade is 64 by 32 by 64 pixels, and cell size is a little bit less than half a meter. Each next cascade is 3 times bigger than the previous one. We use a half-life to ambient cube solution for our basis of irradiance map. It's not an orthogonal basis, but it's very fast to use, to sample from. It's only 3 samplers, and it's really GPU friendly. So because we need our solution to be fast, we chose this basis. It's not important for the method. You can choose the different bases. You can choose spherical harmonics or whatever. It's just we wanted to keep the faster the possible, as fast as possible. So here's a typical sponsor scene with these small debug cubes. Those debug cubes represent the centers of the voxels of the irradiance map, the center of, I would say, light probes there. And each next cascade is bigger than the previous one in terms of the distance, but the resolution decreases. So for scene parameterization, we also use nested volume map, basically volume texture around the camera, same 3D clip map. Each cascade is 128 by 64 by 128 around the camera, and the cell size is 25 centimeters. Again, each next cascade is 3 times bigger than the other. As you can see, that means that our first cascade is bigger size than, of scene representation is bigger size than our first cascade of irradiance map. In this scene representation, we store completely lit results. So it's like you see the whole wall completely lit. In a higher quality settings, we separate lighting and albedo because that increases the quality and the temporal convergence into volume textures. But it's not important. You can get away with only one volume texture. So here's again sponsor scene with our voxel scene representation. The first one is almost looking almost as a sponsor scene. The second but as you can see, the distance is not sufficient, it's not full scene. The next one is bigger, the next one is bigger, the last one is very big in terms of distance, but the quality, you can hardly recognize the sponsor here, which is not very important. We will not use it as a sample for in the beginning of the ray, only in the end. So in order to feel this voxel scene representation, when the camera moves, we feel only new voxels, only new invalid voxels. We keep the voxels in their place if they're valid. We just avoid to move memory. Basically, it's like a texture up addressing or something like that, or cascaded shadow map scrolling, CSM scrolling, stuff like that. You just invalidate the new data without moving the memory. So we fill these new scene voxels with a height map data, with a collision geometry, or lower LODs of the entities. And we immediately light, when we fill them in, we immediately light them with the irradiance map, with the indirect lighting and skylight, and with the sun and direct lights as well. Then each frame, we stochastically choose several thousand of pixels on the screen, and we relit them again. They're gbuffer pixels, so we can use, they will be probably already lit in a gbuffer resolve pass, but we relit them, and with the current irradiance map, with the all direct lighting, and we feedback it back to the scene. So we update the current frame voxel scene representation with the stochastically chosen few thousand of gbuffer pixels. We do that using moving average, which is typical. This provides us the whole feedback loop, because we update the scene voxels with the relit gbuffer pixels using current irradiance volume map, and we update the irradiance volume map using our current scene voxels. It's not only allow us to have multiple bounds, which obviously it will do, partially in the place where you look, but that also help with the issues of not good enough quality of this voxel scene representation. Because if let's say the wall is thin and it's red from one side and blue from the other side, there's no good way you can voxelize the scene there. Let's, for example, see the curtains in the sponsor scene. Right, okay, they are red from both sides, but they could be of the different colors from one side and from other side. That cannot be represented in a voxel scene because there's not enough information. There's too coarse details. But because we update each frame, it won't matter much until, as long as you get to the other side, you see that the color is different, the scene will be updated, and the light will become correct eventually. Additionally, we use environmental probes when they render it, because we dynamically update them, and that provides some more data where the camera hasn't been yet, or before you enter the new room, you probably will get some information immediately before that. For our irradiance map, we do the same toroidal way update, meaning we only invalidate texels of the irradiance volume map which are invalid now, and we have to initialize it with something. And for final cascades, we basically copy information back from the coarser cascades. The information is probably correct. Of course, the quality is not good enough, but initial stage is more or less correct. For the coarsest cascade, for the largest one, we don't have this data because there's lost cascade, and so we have to initialize it somehow. We use trace 64 rays for each of these light probe in the new cascade. So the new cascade is updated, the latest cascade is updated the most rare because of the size and the movement speed, so it is not very intensive. In addition, when we update the fine cascades, we check the texels, the voxels in the irradiance volume map which are intersecting the scene, and we enhance quality there. The newly initialized texels are marked with a special, we have additional texture for convergence weight, and in this additional texture, we mark them with a special value, which means that they haven't been really lit. It's just somehow initialized, in order to lit them as soon as possible, as soon as we see them. When you move across the scene, there will be a lot of voxels, probes, which you will never see, which will never affect anything you see on the screen. You go pass by one wall, and you never see anything beyond this wall. So that helps a lot, but we still need to improve the quality when you see first the probe. In order to make a computation loop, we stochastically choose several hundred visible probes in our irradiance map. I call them probes, but it's actually part of the irradiance map, right? So for these selected probes, we just raycast a few thousand rays, depending on the settings and the visibility of the probe. So probability of selection of the probe for this relighting process will depend on the visibility and the convergence fast, how different it was from the previous one. Of course, this initially non-initialized in the previous slide initial state will be, as soon as it became visible, will be relit. So here's the result of this Ponza scene. As you can see, it's on the left there is an indirect lighting and skylight, and as you can see, it captures a lot of details. It captures bounces and skylight and actually indirect reflections as well. So indirect shadows as well. So the result is very plausible. In order to converge fast, it's important to understand that out of those huge irradiance maps, because they're volumetric, there are a lot of positions there which are not participating in light transfer. They are not intersecting any opaque geometry. It's just a thin air. It's not important to calculate it. It will not affect the result. So in order to converge fast, it's important to have different queries for different probes, for different parts of the irradiance map. First scene never computed has to be computed fast, very fast, and we need them ASAP. We need them on the first time we see them. So we use lower quality, only 256 rays, but the query size is 4,000 or more than that of probe, depending on the setting of probes. For non-intersecting scene probes, we actually don't have to update them at all in order to converge to the result lighting. But we need them because they will affect the dynamic objects, transparent objects like particles, or volumetric lighting. So we still need them to be initialized somehow. So sometimes we update them. We use a lower amount of rays for raycasting them, and we use a very small query size. It's only 64 or up to 128 probes. So we just like lazily update those. We don't need them in order to get the resulting picture, to get result converged lighting. We only need those for dynamic objects, for volumetrics, for particles, for basically forward pass shading. There's a potential issue which happens sometimes when the camera teleports. Everything in the new location, everything is invalid. There is no irradiance data available. There is no scene voxel representation available, and that gives you kind of chicken and egg problem because you cannot make correctly lit results without irradiance map, and you cannot make irradiance maps, at least for skylights and first bounce, without scene voxel scene representation. So we do that a brute force obvious way. We do that in two passes. We voxelize the scene without indirect completely. So there's no skylight, there's only direct lights. And then we calculate the radiance for skylight in this place using a small amount of rays, 64 rays for 64 to 156 rays depending on the settings for only intersecting probes. And then we revoxelize the scene again. Luckily, it doesn't happen very often because usually your camera is not teleporting. It's only when cutscenes or initial appearance of the camera. Rendering with the radiance map is very fast, very straightforward, and covered in a lot of papers. You basically choose the best, in our case, you choose the best possible cascade, and then you sample 3 out of 6 irradiance volume maps, depending on the sign of the normal. And you lead with a square of the normal. You basically add this. So on the border of each cascade, you need to sample from the next cascade and blend between them. So otherwise, you'll see a seam. And it works exactly the same in the deferred and forward passes and volumetric lighting. And it's very, very simple. I provided this code listing here only to show it's really, really simple. It's only 3 samples and very few arithmetic instructions. The idea is well covered many years ago, so it's well known. For diffuse lighting, you're okay with that. It's very fast and that's it. But for reflection, you need to get a little bit more than that because global illuminated scene will be sometimes darker than the nearest environment probe. So basically, when you sample from the cube, you will sample something which has been lit incorrectly or hasn't been lit at all, basically incorrect data. And without any adjustment, this will lead to incorrect reflections. Everything will appear unnaturally bright in reflections, environment reflections, basically kind of wet. So the simple fix is proposed in the volumetric global illumination and Treyarch, which is the name of their paper. And they use irradiance volume maps as well, but they pre-bake those. However, it doesn't matter in terms of the fix for specular. They just rely on this irradiance map information. The idea is simple. You sample from the cube like you used to, and then you adjust the maximum value based on the diffuse information in this specific pixel. This is made an assumption that all the light in the diffuse can appear in specular. So it's very straightforward, simple fix, but it gives good results on most of the surface, especially on rough surface where the reflections are closer to diffuse light in the other direction. We can also increase the quality of the specular reflections on a smooth pixels, smooth surface as well. We can use voxel cone tracing on those. Voxel cone tracing is again slow, but it's way faster for specular reflection than it is for diffuse. Because for diffuse you need a lot of cones, 8, 16, 12, depending on the settings. But for specular you only need 1 cone usually, especially for smooth surfaces. 1 cone is enough. So we also do that only where our screen space reflection pass fails, basically where there is no information, otherwise we use screen space reflection. And we blend them. And voxel cone tracing is only needed if you want to achieve the best possible quality in the case of disocclusion of screen space reflections or in the bottom of the screens. Otherwise, you can go away with the screen space reflection and the brightness adjustment from original slide. So we do it on our highest settings only. Voxel contrasting will, even on specular pixels, will lead to leaking on the thin walls. We don't do anything in order to prevent that. There is no directional blocking information and stuff. So in order to be correct, we use specular brightness adjustment from the rough surfaces for smooth surfaces as well. Our diffuse global illumination solution doesn't suffer from this slight leaking because we honestly trace, raycast these thousands of rays. We don't use simplified statistical cones. And that's almost enough, but of course there is a trilinear filtering issue, which is well known. When you sample from volume map, and the reason why it's very fast is because we use hardware trilinear filtering. Then you'll see some light leaking or dark leaking through the thin walls, especially from the thin walls in the corners. Because on just thin walls you can use normal filtering, which was presented in a Global Illumination Quantum Break paper. It can hide this light leaking, but it cannot hide it in the corners or on the places where normal varies a lot, because it's based on normal. So, and you'll see very ugly light leaking in the corners, like on this slide. If you actually take a closer look on the left wall, lighting isn't correct on the wall at all, not only in the corner, because when the normal is moving, and there is a normal map on this wall, the light is totally incorrect. It's wrong. This is very thin wall, but unfortunately we do have those, and we need to do something with this. So what we did was quite straightforward. We had convex meshes for indoor volumes. Basically, it's a list of planes which close the indoor, and these convex meshes allows us to have two possible enhancement. First, we can sample position which are updated with these convex meshes, not allowing to trilinear filter across the plane of the convex mesh. And the second potential solution would be to use two sets of radiant volume maps, one for indoor and one for outdoor. That would be provide even better quality, but would require twice more memory, obviously, for radiance map. So we have chosen the first method because of its simplicity and because of the memory footprint. But obviously, this filtering sample location increases the performance cost of the lighting with the radiance map. So again, light leaking picture and light leaking picture with the convex offset filtering. As you can see, not only light leaking in the corners disappeared, but the left wall is way more accurate and more reasonable lit. This solution isn't perfect, but it's very good, and it doesn't require a lot of artist's time because they don't have to check what they have done, unlike many other proxy geometries. They just need to fill the walls with the convex meshes, and it's just work. So, and it's not important to do everywhere. It's just needed where you have thin walls. There's another potential issue which is caused by our voxel scene representation, not by our radiance map, but our voxel scene representation, which is typical for all voxel scene, like voxel contrasting as well. When you voxelize the scene, voxels tend to be bigger than the pixels they represent, so the opaque geometry will inflate, it will become bigger. And in some small holes, small windows, they can completely disappear. In this case, they disappear not because the window is very small, but because there's something inside the window which became a lot of voxels, and suddenly there's basically no light coming from the sky. As you can see on the right slide, it's just because there's no hole there. So in order to fix that, we add very simple another type of volumes. A very simple solution, we add holes which will never be filled with scene voxels. We just not voxelize a pixel or a triangle in the place which is covered by this volume. And as you can see, there is a hole now again, and the light is fixed. The light is coming through the window now on the wall and on the ceiling. Everything is there. These are probably the two main issues with our solution, but there is some other not obvious tricks and enhancements we did. We use cluster array direction in order to avoid divergent branches in different compute threads. We cluster them by the size of warp of the hardware. And we use current frame occlusion to not lead completely invisible probes, completely invisible parts of the irradiance map. In your engine, you'll probably have some kind of visibility solution for occlusion, but in this case, you can just rely on the GPU depth buffer information because it's already good enough. You just make a hierarchical Z buffer with it and use it. So there's one additional trick we used because we, instead of storing binary alpha information, like if there is voxel in the scene representation or if there is no voxel in the scene representation, we store transparency. That allowed us to fix too unnaturally dark foliage, because foliage geometry is very azure. There's a lot of small leaves there, and during voxelization they can become completely opaque, and the light will not pass, and you cannot not include that. Otherwise, there will be no indirect shadow from foliage. So instead, we add transparency information, and when the ray traversal during the light integration, when the ray intersects with such voxel which isn't completely opaque, we just add the data from the color and go on, and we will multiply all incoming light after that by the transparency in the pixel, which allows us to get on the bright side. It allowed us to get kind of volumetric lights. So if you just make a transparency low, and you add more light, then every ray which traverses through this voxel will receive light. So we use that for creating volumetric lights in the fires. You can use modern hardware capabilities to improve quality. Because again, raycasting voxel grid suffers from inaccuracies in precision of heat location mostly, but also with the quality of the data it's sample. You can use modern hardware ray tracing to just raycast the rays. Basically, we use collision or LOD data. We don't use shading of those. I mean complicated shaders. The issue with ray tracing is there's a lot of materials, a lot of different materials. So we don't use that. We just need the heat position, heat normal, and we sample albedo from our scene representation. And in that case, we can shade the pixel way more accurate, and the whole issue with the small windows and trees just disappear. It's just walk as is without this information. So here's a small video showing the result effects. As you can see, there is a global illumination capturing dynamic scenes, dynamic lights, and multiple bounds, and skylight as well, which is the most important thing. And it works very, very fast. It also allows us to capture even short-time global illumination effects. As you can see, the ceiling became lit up when the door has opened. It hasn't been done. We haven't done anything special with that. It just works because the convergence speed is very fast, and it works in almost half millisecond on Xbox One X with a 4K resolution, and 1.6 millisecond. The video is a little bit outdated. 1.6 millisecond on Xbox One in the full HD resolution. So which is also very important for us. The quality of our solution is very adjustable. It's not just like you plug in 6 milliseconds or there's nothing else. You can support low-end PCs and ultra high-end hardware with the RTX capabilities there. And in both cases, you will not be in advantage if you're playing on a low-end PC on low settings. It's very important for competitive PvP game to keep this. Otherwise, everyone will have to go, switch off everything, completely remove all the features, and we cannot allow that because the game will be not interesting visually. So our solution is very scalable. You can scale the detail size, you can scale the temporal convergence speed, and you can scale the quality of the sampling data. It allows us to have dynamically destroyable buildings and dynamically buildable fortifications. And of course, as there is no pre-bake, the iteration for artists and lighting artists is really fast. Obviously, location size is not limited to anything because we have all data information only around camera. Number of light bounces is unlimited if you look in that area of the world. And number of light sources and type of light sources will depend on your engine. So in our case, it's actually 8,000 lights of different types. There's no pre-bake needed. There is no additional client-side data, and there is very small additional asset production overhead, these two types of volumes. This allows us to have daytime changes, destruction, construction. There is some certain limitation to this technique, which is the negative side. The fast-moving objects, dynamic objects, would not participate in the light transfer. Obviously, they can't. So they can only receive lights. We cannot support very dynamic lights, like blinking light or flashlight. It can be in the game, but it cannot be part of the global illumination solution, because otherwise you'll see the temporal effects. We chose only several hundreds of props, and you'll see the trail of the bounce of the light. So your engine has to be kind of deferred. It doesn't have to be really deferred, like completely deferred. It can be forward, but you need to additionally render lighting data, like diffuse lights. And these, which you probably already have, this velocity in the G buffer is also important in order to mark pixels which are dynamic. Some of your collision data or lower LODs of the entities should be available in GPU. For low LODs, it's not an issue. They are probably on GPU already. In order to make collision data on GPU, you'll have to put it there, but it's not very big penalty. Memory footprint of the solution itself is less than 32 megabytes. Most of it is a scene representation, and scene representation can be up to 33 megabytes itself if you want improved quality by separating the lighting and the albedo. And in typical medium quality, it's all of it combined is 32 megabytes. Out of which 16 megabytes is scene representation. The performance cost is mostly total performance cost is 1.6 milliseconds on Xbox One, and in full HD. And most of it goes to recomputing of light props of radiance volume map each frame, which is good because you can async compute it. You can put it in async computation, and that will be, of course, if you still have computation resource, that will be virtually free for you. It can even be completely disabled. That will decrease the quality of the light. You will not get the small shot global illumination effects, but you will have skylight and single bounces still. The lighting addition cost is about 1/3 of a millisecond. By additional cost, I mean, because we have a deferred engine, we already had some lighting pass. And by additional cost, I mean the difference between original lighting pass and adding this technique. The whole, unfortunately, is a little bit bigger than that, but that's not part of the solution. The movement of the camera will will spike sometimes from up to 1 millisecond in our case, in our game, but it doesn't happen each frame. It's usually less than 1 per 10 frames or less than that. So amortized cost is a little, is less than 1/10 of millisecond. So, like again, completely synced multiple bounce solution will be 1.6 millisecond in the full HD on Xbox One. And totally completely asynced or one bounce will be less than millisecond on Xbox One. It is possible to make an even further improvement for using this technique. Our solution is to perform per pixel ray tracing. Instead of radiance map, or at least on a closer distance, instead of radiance map, you can raycast rays from pixels. In our experience, from 4 to 6 rays per pixel is usually okay, if you have some denoising, of course, and temporal denoising. And in a 4K resolution, even on the most powerful video card with the RTX support now, it will give you like 20 millisecond additional cost, which is prohibitively high, but you can render it in half resolution as well, and that becomes reasonable cost. With the ray tracing per pixel, there's obviously no light leaking through radiance map because you don't use the radiance map, you know, to achieve the result in the pixel. So it's way more detailed light because your minimum detail you capture depends on the resolution of a radiance map if you use it. If you use a per pixel, it's just there. And of course, you can increase the quality combining with the screen space techniques, like using SSGI with a combination of our solution. You need to keep track of the size of the feature you're capturing, because screen space radius will become very high in meters very soon. So you need to keep track of that in order to add screen space effects only where the size of the feature is less than the radiance map. Basically, that's it. Some questions? Okay.
Great stuff. Oh, sorry. Somebody else.
Go on.
If I get it right, you only update the lighting in the voxels when you see them on the screen, right?
Scene voxels?
Uh-huh.
Yes, we only update scene voxels when we see them on screens or when we render the environmental probe.
Right. Mm-hmm. Thanks.
So that's the whole trick, basically, because you have all the information in the gbuffer. You can update the data easily. It's very, very cheap. As you can see on the performance cost, it's less than like 200 of milliseconds. It's very, very cheap. But of course, you can do it only where you see it. Otherwise, you need to do something else. But that's the whole trick of the solution.
Thanks.
Okay. Thank you.